Hi everybody. Right now I'm going to be doing Sipser Exercise 4.7. So the problem says, let B be the set of all infinite sequences over the set 0 and 1. And we need to show that B is uncountable using a proof by diagonalization. So the first thing we need to ask ourselves is, what exactly do we mean when we say that a set is countable? Right. So according to the book, it's page 203. I think it's like definition 4.14. It says a set is countable if it is either finite or it has the same size as n, where n is it's a set of natural numbers. So there we go, n, where n can take on values such as 1, 2, 3, and so on. So the way we can determine if two sets are the same size is using a technique called diagonalization. So to kind of put it in a nutshell, so let me give a quick example. So let's say we have two finite sets. So we have one set A, and we'll say A contains the elements 1, 2, 3, and 4, and B equals 2, 4, 6, and 8. So we can say that two finite sets are the same size if we compare one element of A with one element of B. And as you see, we can do that. So A, we compare 1 to 2, 2 to 4, 3 to 6, and 4 to 8. And when this occurs, we call this having you can say that two sets have a one-to-one correspondence. Alright, so now that we have a basic understanding of what diagonalization is, now we need to get back to what the problem is actually asking. So let me erase what I got here. There we go. So we have B, which is an infinite sequence. So let's just list the first few elements of B. So there's our set B, and we've got the elements of B1, B2, B3, B4, all the way to infinity. Alright, and each of these values in B can take on values of 0 or 1. So we can write that. So B of I is an element of 0 or 1. Alright, so in order to use diagonalization, we're going to be using a proof by contradiction. So the first thing we need to do is suppose that B is countable. So let's write that down. So now we know from our earlier definition that if B is countable, then we can define a corresponding function f that will map the set n, which remember contains just one giant set of all the natural numbers, a function that will map n to our set B. So let me write that down. So we have some function f that will map n to B. Remember, we're trying to get that one-to-one correspondence. So let's redefine f in terms of n. So we'll define small n as an element in our set of natural numbers of big N. So let me rewrite that. So we'll say that big N. There we go. say that n is an element in big N, and we can therefore rewrite f of n where n will map to b. So we can then write f of n, right, as a set of elements from B. So B of n, 1, and so on. So what we're actually doing is setting up a matrix form of our function f of n. So let's write a generalized version of what we're doing in terms of our just plain b's. So we got n, and we have f of n. So 1, 2, 4, and our f of n. So now I'm just filling in the b values. Alright, so here's where the proof by contradiction comes in. So let me rewrite this kind of generalized matrix I have here in terms of real integers. So let me move this information that I have here up to here. So f and I will erase what I have over here. Alright, so I'm going to rewrite this with actual concrete values. So we have n, whoops, we have f of n. So for n, 1, 2, 3, 4, keeps going. So I'm just choosing arbitrary values here. So I've got 1, 0, 1, 0, 1, 0, 1, 0, 0. Right, and these just keep going. So now I need to figure out where the whole contradiction thing comes in. Alright, so let's create a new sequence. I'll just call it C. And C will contain all the values that are along the diagonal of our matrix. So for in this case, oops, there along the diagonal we have 0, 0, 0, 1, and of course that just keeps going on. So C, the elements of C will actually contain the opposite bits that are located at some index in the matrix, some index B, called B I of I. So along the matrix, along the diagonal, everywhere we see a 1, a 0, we'll make it a 1, and everywhere we see a 1, we'll make it a 0. We're just flip-flopping the bits along the diagonal to create a new set that we're calling C. Right, so then C equals 1, 1, 1, 0. Well, we know that keeps going on. Alright, so how exactly does this help us? So we know from our definition up here, for b to be countable, our function f must map all of our natural integers in n to the subsets of b, such that every subset occurs in the list. So every possible combination of zeros and ones will be somewhere in the list. So if we look back at the sequence C we created, right, we can see that C could never be equal to the first row of values because we changed the first bit. So then we look at row 2. Well, C can't be equal to row 2 because we changed the second bit, and so on and so forth. And this goes all the way up to n. So even at n, the C can never be equal to n because we changed the n bit. So C will never be in our list, regardless of how far we count as n approaches infinity. So therefore, we say that B, which is our original set, is uncountable. And there we go.